do a mental experiment real quick here. Imagine, for a second, let's forget all about robotics. Imagine that you're a software developer. Imagine that you've, imagine that you've worked.
Now you're
No.
yeah.
Let's just step back though and imagine you're a software developer and you're working on something that's been, it's great. Let's say you're working on something that can analyze stocks and help you make a lot of money. You want to give it to your friends and family. You spent a year, let's say, toiling away on this thing. You decide, I want to give this out. I want to start transferring this technology to other people so they can use it. And then when you go to zip up this program and give it to somebody else, you all of a sudden, your blood goes cold because you realize this program only works with your hardware system. It only works with your hard drive. It only works with your motherboard. And you can't give it to anybody else. And all of that work that you've just done is going to stay right there on your computer and really not go anywhere. You guys know where I'm going with this. That's what we're doing in robotics right now. There's no transferability in robotics. There's none. Everybody's kind of an island. Everybody's rebuilding the robotics wheel by themselves. Now, shouldn't feel ashamed. This is natural. This is just the way it is. This is just where we're at the moment. But that really is what's happening. And that's why standards are so important. Because with standards, we can start to, it gives us three things. It gives us more modularization, because now people can focus on hardware, and they know that it's going to plug into other components. It gives us transferability. Again, see, I didn't get robots. I just got little wood guys. So people can start trading technology. And what that really does, it allows people to start standing on each other's shoulders. And that hasn't been going on. And that is the core reason why robotics isn't moving as fast as it possibly could. In the end, what it allows us to do is stack technology. And that's just a little example of different types of software programs stacking on top of each other. That's what standards brings to the game. It gets us to software concentration in the end where we can really start to explode in robotics. So let's talk about that in earnest. You know, for 2 or 3 years now we've been talking about standards. You know, there's a lot of rhetoric about it. And it's sort of the pink elephant where we would talk about it, but we don't really get into it. And I want to do that today. I want to talk about some real, concrete examples about where we need standards and how we can use them. The very first thing that we have to do is abstract the code from the hardware. Right now, the code and the hardware are too intricately tied together, and that's because everybody's working as their own islands. It's very natural to make something efficient, so it's basically an impulse of an engineer to tie things close together. So we need to separate those two out. We need to start thinking more in black box functions so that when you think about doing something like moving forward 5 feet, you don't think about talking directly to your hardware. You think about asking an algorithm library to do that for you, and it talks to your hardware. We need to abstract those two things and split them apart. So here's a really simple example of a system, and we're talking about how we separate these two things from each other. You have a robot objects model that's up there in the top right. There's my fancy little star. You have some sensor libraries and some controller libraries that talk to hardware. So that blue line represents your computer or whatever processor system you're on. Underneath there you have a breakout board or your motherboard externally that talks to your different daughter boards, which are your sensors and controllers. You can't really separate the two until you put a layer in between your hardware and your software. The way we do that is by a robot object model. And that's the first place that I believe that we need a standard, so that different people working on different systems can all know exactly how they're supposed to store their data, how they're supposed to interact with the data, and when you write a software program, you can then transfer it to somebody else because they're going to have their own robot objects model they're working against. So here's how it works. Imagine that you're working on a robotic arm in Chicago, and that someone over here is working on, Joanne, you're working on a robotic arm in Japan. And the two of you are working on a similar problem. Let's say you're just trying to solve some sort of picking and packing behavior. Right now that's a problem because anything that you work on when it comes to algorithms, it's going to know specifically what your arm is, what the size is, what controllers you're using. It's intimately tied together. When you have an object model that you work against instead, what you have is a live instance of your robot when you have runtime. And this will be stored probably in some sort of markup language, not when it's not in runtime, something like robotic XML, if you will. That stores two types of data in there. It stores static data and it stores live data. Your static data is things like, what are the length of the pieces of my arm? What's the kind of motor that I have in my joints? What is the controller type that I have this connected to? What is the different positions for 0, 90, and 180 degrees? And in terms of like a controller, how is it going to see that so it knows to talk to my motor? Live data is things like current position of the arm, current status of your sensors and the data that's coming in. So it's storing these two different things. What happens is when both of you fire up your robotic arms, it pulls in this XML file and creates an instance of your robot. So now when you're talking about moving things around, you're talking about in terms of distance or in percentages of the arm's size. If you're doing that, you talk to your algorithm library, And it's going to go and look up at your object model and say, how big is your arm? Okay, if I want to move XYZ from here to here, it's going to go ahead and figure that out for you, and it doesn't have to know exactly what hardware you have. It's just going to read your dimensions and calculate it for you. What it does is going to hand you back an array of data at that point. And let's say you want 100 iterations to get to that point. It's going to do inverse kinematics, and it's going to do the calculations and hand back those angles. It's your job, now keep in mind, it does not talk directly to your hardware. It's your job as the person writing the code to decide when that data goes to the hardware, when you make that action. So for instance, you might want to preload a bunch of actions ahead of time and store them for later for efficiency's sake. So again, the one thing that's missing up here is that you don't see the algorithm library. So what happens is when you decide you're going to execute that code, make it happen, you're going to write that stuff to the object model. And on the left side, you see the control library is going to see that there's a change in the object model and know that you've just decided to change one of your angles. And it's going to go ahead and take another look into the object model and say, okay, we want to move a joint. So what's inside of there? You could have more than one motor, you could have a single motor, you could have servos, DC motors. It's going to go in there and it's figure out what that data is. It's going to, okay, we've got a servo, and it's attached to a fidget controller. Let's say it's on port 3. And what is 0, 90, and 180 degrees? So I can do my calculations and figure out how this works. And it's going to go down and talk to your hardware and make that a reality and make it happen. So you can see where we're going with this. So if you have robotic arms, the robotic arms could be different sizes. If you're working in percentages, it doesn't matter. You could have an 8-foot arm running off the same software as a 5-foot arm. You know, when it comes to, let's say, navigation with wheeled robots, you could have a robot that's 2 feet tall, and you've got large wheels on it, and different size encoders and different controllers than yours. You could have a small robot that's this big, but if you're both working on navigational software and vision software, you've now abstracted the hardware from the software. So it's thinking in terms of, I'm going to go 5 feet forward, turn right, go another 4 feet, turn left, et cetera, et cetera. You can have completely different hardware, but you guys can still work together. That's the transferability we're talking about that we need, and a standard that can make that happen. So that's the first place, is in the object model. If we can get together as a community and create a standard, this sort of model doesn't care about what software you're using or what package you're using. You know, you can be in whatever language you like, you can be on an operating system you like. A lot of times you hear about standards, somebody's chosen a language. They've chosen an integrated development environment that they've built from top to bottom. This has nothing to do with any of that. You can be in your favorite development environment. You can be on your favorite platform. It doesn't matter. This is above all of that. So, you know, if you want to be in MSRS, that's fine. If you want to be in Java, that's fine. We do all of our development in Visual Studio, you know, which is not made for robotics, but we get away with it just fine because we work against an object model.
So this is at a different layer than MSRS?
I would say that it's solving a different problem.
That's a lower level thing.
Yeah, I would say that it's solving a different
communication level, protocol level, and this is
absolutely.
Semantic level.
We get that question a lot, and my answer to that is that the MSRS, Microsoft approached it from an operating system mental standpoint, and that's the problems they were solving, was communications, something that, yeah, multiprocessing, and I think they built something that's very good and has a lot of places. So, the second place that we would need standards, down there at the bottom, in between the daughter boards. So if you're going to have a lot of different people making modular components, those components have to be able to connect to each other. People want to be able to say, I focus on distance sensors, or I focus on encoders. They don't want to have to build an entire system, once again, in order to do that. So we want to be able to have these things plug in together. It seems like I2C is kind of the top dog at the moment that a lot of people are using, and it may be that or maybe something else. But if we expose those protocols and how these boards should talk to each other, we now start to build a full vertical that everybody can plug into and not have to go ahead and build the entire system top to bottom. So in my opinion, it's the second place that we need standards. If we have those two areas, if we create standards, then we're golden. You know, and like I said, if we use more computers in our systems, you know, we can start to adapt with the bridgeware that's used in the middle there. So bridgeware, again, is what gets you from a computer to robotics I/O. And there's a couple players out there now. I think we're going to see a lot more of it. I don't think you need a standard in there. I think that could stay proprietary. It really wouldn't matter. What you need to do is open up those protocols in the bottom and on the top. You need to tell people, this is our API and this is how you use it. And at the bottom there, when you've got your main board, let's say, it's got its I/O on it, that stuff should be released too so people can plug into it. And what bridgeware companies are doing is taking care of that nasty middle ground that's real confusing and problematic. It's a lot of trouble. And so when they take care of that for us, great.